Hello and welcome everyone to this presentation. Today we're going to be talking about scale testing the network control plane, in particular HashiCorp Consul and the Consul global scale benchmark that we did in April. So a bit about myself. So my name is Mishra. I'm the technical advisor to the CTO at HashiCorp. So I work in the office of the CTO, and the picture that you see of me on the slide there is me rehearsing for opening HashiConf EU in Amsterdam in 2019, which was the last in-person event there. I still remember meeting everyone in the crowd, and also a lot of people in the community. That was really a privilege for me to open the conference for Mitchell and Armand there. Hopefully we can get back to that. For now, we'll try to make the most of this. So yeah, I work in the office of CTO on strategic initiatives internally with the product and engineering teams, and also externally with our partners like AWS and Microsoft. I'm a computer engineer by training. So I went to school for computer engineering. I've done software engineering and operations engineering. I kind of empathize with both developers and operators and understand this empathy towards delivering software. I also work a lot on open source, and I love open source. And here's a few projects that I work on. You might see me on GitHub in the past few years here. All right, let's get into the agenda here. So it's quite a straightforward agenda. So first, we'll talk about some of the history of HashiCorp and benchmarks. And then we'll talk about scale testing Consul, in particular with the Consul global scale benchmark that we published in April. And then I'll give you a background on service mesh, in particular the components, especially the control plane that was the focus for this benchmark. And then we'll talk about the benchmark setup, the benchmark tests and the results, and talk about some of the learnings from it. It's quite straightforward. So yeah, HashiCorp and benchmarks. So in, I think, March 2016, we did our first public benchmark and published the results, which was on Nomad. We did the million container challenge where Nomad scheduled 1 million containers in 5 minutes across 5,000 hosts on GCP. The Nomad team outdid themselves again. So they more recently released a benchmark in December 2020 where they scheduled 2 million containers across, I think, 6,100 hosts across, 10 different AWS regions in 22 minutes, which was amazing. So you wanted to bring in the same scale and kind of concepts into a kind of focus and focus them on HashiCorp Consul and specifically the service mesh. So why do benchmarks, right? That's one of the big questions that one might ask. So here's a video of Airbus A350, and we talk about the stress testing on the wing here. So essentially the wings bend, to a really large extent, more than anything that a traditional flight would ever experience. So you'll notice here the wings bend to about 35 degrees or so, which is really, really impressive, the amount of force that put on this wing. And there are other aircrafts that might also do this test, and they might go up to maybe 15 degrees or so and then snap. But those aircrafts are safe as well to fly because traditionally a flight might never experience such a stress on the wing. But my question to you is, which aircraft would you like to be on or take flights on? Is it going to be the Airbus or the aircraft that maybe snaps at 15 degrees or so? So the answer is probably the Airbus, and this is where these concepts also could be directly applied to products and software that you use every day. So now I want to take a step back and talk about service mesh and talk about some of the components of a service mesh. So let's say you have a service A and you have a service B. And service A wants to talk to service B. They're both in the service mesh. So service A will do a local host call to its local proxy that's running alongside it. This might be a sidecar container. This might be a systemd job on a VM or Nomad allocation and so on. And then the proxy is responsible to finding a healthy service B, and it'll make a mutual TLS call using certificates and so on, and make a mutual TLS connection and connect up to the proxy, the service B proxy. The service B proxy will forward that request up to service B, right? And essentially, this is how service A will get to service B. It doesn't need to know the IP address of service B. It'll just make a local host call, and everything else is the responsibility of the proxy. But here, the interesting thing is something needs to configure this proxy. So this is where the control plane comes in. So the control plane is responsible for providing service discovery data, maybe certificates and so on, things like in policy rules, traffic shaping rules and so on. And so it is the kind of the component that's responsible for maintaining state in the system, and it's the highly available component of the service mesh. And then you have the data plane, which is just the proxy itself. It's responsible for routing packets from one place to the other after being configured, getting the configuration from the control plane. So this is why we made a focus on the control plane itself, because this is the resilient, like kind of the highly available component of the mesh. And this was the main focus with the Consul global scale benchmark, the control plane scalability and understanding how Consul responds to really large scales. All right, let's talk about the benchmark itself. So we did this in, I think, February 2021, and we published the results in April. So we did two important propagation time tests. One was the endpoint propagation time, and the other one's intention propagation time. So for the endpoint propagation time, we had 10,000 hosts on EC2 on AWS, and we scheduled, I think, 178,000 containers. These were applications that were running on the cluster using Nomad. And then we made all of these containers and applications depend on one upstream, common upstream, and we changed that upstream. Now, what I mean by changed is we either deleted it or added it. In this case, I think we deleted the upstream service. So essentially, that triggered a change in all of the 178,000 proxies. And what we saw is 96.6%, which is about 172,000 proxies, updated the configuration within 1 second or so. And this was all done using 5 Consul servers in the cluster. Next test was the intention propagation time. So intentions in Consul are ways to define access permissions of how a service can talk to another service in the mesh. These might also be traffic shaping rules and so on. So for example, whether service A is allowed to talk to service B is something that you can express using an intention, essentially. So what we did here is we created an intention that would affect 9996 nodes. So essentially 9996 agents that were running on these nodes. The 4 nodes that we missed out of the 10,000 were running workloads that might not be related to this intention change. So as soon as we changed the intention, in this case we created an intention, the propagation time from the control plane all the way down to all Consul agents was about 900 milliseconds, which is quite impressive for the extent that we were running it. We had about 5 Consul servers again here, powering the control plane for this experiment. So those are the results, and now we kind of get to a stage where how did we get to those results, right? So let's talk about the benchmark setup. So the benchmark setup actually was quite straightforward. There was no secret sauce that we used, a secret service that we used to optimize and get these results. A lot of the products like Consul and Nomad were running almost default settings with some minor optimizations that I can talk about in the next few slides here. So essentially, we had 5 Consul servers. This made up the control plane for the service mesh, and the EC2 instance that we were using was C5, I think C5D 9x larges or so on. And we had about 36 vCPUs on these boxes with 72 gigs of memory, and they were spread across 3 availability zones. And then we had 3 Nomad servers that made up our scheduler control plane. They were decently sized as well. Then we had 10,000 Nomad clients. Each Nomad client was running a Consul agent inside it, alongside it as a systemd job. And these clients were about C5x largest, so 4 CPUs of vCPUs with 8 gigs of memory, again spread across 3 AZs. And the way we kind of created these clients were to use auto-scaling groups. So we created 2 separate pools with 5,000 nodes each, which made up to the 10,000 node count on the clients here. Then we had 100 load generators. So essentially, these load generators were responsible for just testing whether all of the service configuration in the mesh was correct, and service-to-service communication was okay. So essentially, we routed traffic to a bunch of workloads and tested out the service mesh. And again, I wanted to note here is that the data plane scalability was not the focus for this experiment. So we didn't care about like how fast, how much requests we could put through the system and so on, which of course you could in this really large system. You can go through a really large number of requests. And then all of the setup was in US East 1 in the AWS region. Next, I want to talk about the workload setup for the benchmark. So essentially, wanted to mimic something in real life and kind of bring that into our benchmark. So essentially, kind of mimic the microservices world that a lot of organizations are in. So we created a 3-tier service architecture. Essentially, we had service A, service B, and service C, the 3 tiers. And service A was dependent on service B, which was dependent on service C. So you'd call out service A, which would call out to service B, which would in turn call out to service C, and you get a combined response. And these applications were basically just returning some text back, so weren't doing much in terms of just workload. So there were about 1,000 unique services per tier, so which makes up to about 3,000 services in the cluster, unique services in the cluster. And each tier had a number of service instances. So we had 10,000 service instances in tier 1, we had 83,000 service instances in tier 2, and we had about 85,000 service instances in tier 3, which makes up to about 178,000 total service instances running in containers in the cluster. Now, this does not account for the sidecar proxies. So if you bring in the Envoy sidecar proxies, this number goes up to 356,000, which is just 178,000 times 2 in total service instances and Envoy sidecar proxies. Now, each and every service instance and the Envoy sidecar proxy was registered with Consul, and there were health checks that were going on just to basically monitor these applications and the proxies. So this is what the service layout looked like. The 3 tiers, you can see tier 1, it goes all the way from A1 to A1000, which is 1,000 each. And then A1 is dependent on, it calls out to B1, and B1 calls out to C1. And the same thing for tier 2 and same thing with tier 3. The unique thing here is that all of these service instances were dependent on one upstream service called service Hey. Now I know you'll talk about this name, like how did you come up with this name? I know this is very unique name, right? Like I can take full responsibility for this naming here. So essentially, if this service Hey was to change, all of this 178,000 proxies applications will need to update their sidecar proxy configuration. All right, so now let's talk about the benchmark tests and results. So how did we scale up to actually start running all the workload? So we used Terraform, essentially a Terraform apply to start creating all the infrastructure. So we created all the VPC resources, the subnets, all the underlying infrastructure that you need to run this benchmark. Then we created the control plane for the service mesh, which were the Consul servers. Then we created the Nomad servers, which was the scheduler. And then we actually scheduled the workload as well using Terraform. So we applied the workload on Nomad using Terraform as well. But we queued all the workload first. So essentially what we did is, before we created any of those 10,000 nodes, we queued everything up. So in Nomad, you can queue jobs. And then when nodes are available, Nomad automatically schedules workload on them. And we were using a spread scheduling algorithm, so essentially spread the workload across those 10,000 nodes. The reason for queuing these jobs was because we wanted to make sure we optimized for every billing second that we got. We were on a budget, so we couldn't rerun these things multiple times and want to make sure everything comes up okay. So we wanted to optimize, all the kind of the idle time of these instances as well. So and then, so in terms of creating the 10,000 nodes, we used the 2 auto scaling groups with 5,000 nodes each. Those came up almost within minutes. Amazon, when you ask for 5,000 or 10,000 nodes, they just give it to you. So in order to avoid this thundering herd problem, well, all 10,000 nodes or so, like approximately that, would try to join and register services and so on at the same time. What we did is we added a random delay up to 26 minutes on every node. So when a Nomad node would boot up, it would actually choose a number between 0 and 26, and then just wait for that time, and essentially then finally join the cluster and then register themselves. So it kind of gives you a very graceful scale-up action. It did make our scale-up a little bit delayed, but it kind of gave us that, that responsiveness. And doing this actually helped us and kind of instilled confidence in the benchmark. So essentially, we wanted to optimize for success. We were restricted by the budget. We couldn't rerun these things multiple times. So we wanted to make sure we get it right, most of the time here. So here's some of the graphs of what the scaling up looked like. So you had, it took about 51 minutes for all of the 10,000 nodes to come online. This includes the nodes joining and all of the workloads to also be scheduled on those nodes. So both of these things, and everything registered, everything good to go. One interesting thing here is that you see that CPU usage graph. So during the scale up period, you see the CPU usage goes up to about 43% or so. And that's due to all of the service registrations, the node registrations, and also certificate signing requests from the clients to talk to the control plane, and also for the services that were being scheduled that were wanted to be part of the mesh will also get unique certificates to be able to do MTLS in the cluster. So essentially, those certificate signing requests as well were done by the servers. And as soon as you see that you hit the 10,000 nodes and everything is scheduled, the CPU on the control plane on the servers, it just basically it goes down and stays at about 5 to 10% or so on throughout the experiment. So now I want to talk about the results, right? So what were the results when we did the endpoint propagation time test? So essentially what we did is, as I mentioned before, the service hey, which was the common upstream, we just removed it. We deleted that from Nomad. Essentially that triggered an update. So all of the 178,000 proxies needed to update their configuration at the same time. So what we saw is 96.6% of the total workload, which is about 172,000 proxies, updated their config in under 1 second. On the right, you see the graph of the kind of the latency distribution here. On the left, you see the table that kind of showcases the latency distribution as well. And you can see, P96 is about 564.2 milliseconds or so. One interesting thing to note here in the graphs is this agent coalesce timeout. So essentially in Consul, we had a 200 millisecond timeout that's built into Consul. So what we do is we wait for changes up to 200 milliseconds and then coalesce and batch all of these changes and send one change to Envoy to reload its configuration. And this is basically avoids Envoy to get triggered updates all the time, especially when there's proxy boot ups and so on, and gives you that efficiency in terms of the proxy here. So this timeout's already built in, and of course, if we were to remove this timeout, you might see better results here. I want to talk about the long tail that you saw in the previous slide with the latency. So there's about 3.4% of the proxies that took minutes to update. So in some cases, 5 to 10 minutes, after the endpoint event had happened to update the configuration. And this delay appeared to be a transient network disturbance, and that we saw at this scale. So essentially, you're running 10,000 nodes, and that too in the clouds. In the clouds, essentially, you will see some form of network disturbances. We saw TCP connection drop-offs where the agents would go into a retry back-off. Some agents failed repeatedly to connect to the servers due to transient network timeouts, but due to repeated failures, they were in back-off state and took a minute or more to reconnect. Some agents remained connected to the servers but saw packet loss and TCP retransmits. Next, I want to talk about intention propagation time test. So essentially, intentions in Consul are ways to define access permissions between services. Whether a service is allowed to talk to other services can be defined using an intention. So we created an intention that would affect 9,996 nodes essentially. And the 4 nodes that are missing here were not running workloads. So essentially, as soon as we created an intention, all the way from the control plane, the propagation time down to the Consul agents was about was under 900 milliseconds in this case. On the right, you see the graph for, again, the latency that it took. Again, the x-axis here is the time in milliseconds. On the left, you see the latency distribution table. You can see P99 is about 815.2 milliseconds. Not only did we run this test on Nomad, but we also ran this on Kubernetes. So we created a 500 node Kubernetes cluster, had about 1990 service instances running on them. They were all kind of dependent on this one common upstream service, very similar to what the example that we saw earlier. So we changed that service. In this case, we created that service, so that registered itself in Consul, and that caused a change that would lead to 1990 service instances updating their sidecar proxies. So that took just under 700 milliseconds for all of these 1990 proxies to update themselves. And you can see some of the graphs here. So on the right, you see the propagation time graph, and on the left, you see the total running pods in the Kubernetes cluster. Next, I want to talk about the benchmark data collection. So we had a lot of data, as you can imagine, with a benchmark of this scale. We used the Datadog platform for all of this. So we collected stats-D data from Consul, Nomad, Envoy proxies, Kubernetes, load generators, logs from Consul, Nomad, Envoy proxies again, and the application itself. We used a fake service application. You can find it on GitHub. We also had APM data for the application, essentially to generate service-to-service traces and to test out whether the service mesh was configured correctly, and also generate latency graphs to test out the data plane here. So Datadog processed about 1.8 billion log events throughout the kind of the period of the experiment, all the way from lower node counts all the way up to the 10,000 node count. All right, with that, I would like to thank our partners. Big thank you to AWS for giving us the credits and the support to run this experiment, to Datadog for giving us the platform to store APM data, logs, and StatsD data, and all the credits to run this and perform this experiment. So big thank you to both our partners here. And if you want to check out a detailed version of this report, so this talk is a 20-minute talk, only highlights a few portions, important portions in the report. So if you want to read it in detail, you can go to hashicorp.com/CGSB, which is Consul Global Scale Benchmark. So all of the configuration for the benchmark is also open sourced on GitHub. So this includes all of the Terraform configuration and the service specifications for Nomad and Kubernetes. This is all available under the HashiCorp GitHub organization. So you can go to github.com/hashicorp/console-global-scale-benchmark. If you don't want to read the detailed report, you can definitely check out the HashiCast episode on Consul Global Scale Benchmark that features Paul Banks, who is the principal engineer in Consul, who worked with me on the experiment. This goes into some of the insights and behind the scenes of the experiment and some of the details. So definitely give that a listen. So thank you so much. I really appreciate you all coming to this presentation. A special thank you to the Consul product and engineering teams for building a product that can scale at this extent. Also, a special thank you to the Nomad product and engineering teams for giving us a scheduler to actually run this test at this scale. So thank you so much. I hope you all have a great HashiConf and stay safe.